Hi, everyone. Hope you're having a good morning, good afternoon, or good night. My name is Kevin Lance, and I'm the Director of Biologics and Gene Therapy Marketing at Unchained Labs. I'll be your moderator, and thank you for joining us today. We'll have a Q&A session at the end of the presentation. So to ask questions, all you have to do is click on the Q&A button in the Zoom navigation bar at the top or bottom of your screen and type in your question. When submitting a question, please avoid clicking on the anonymous button, so that way we can reach out by email afterwards if we aren't able to get to your question. And we will get to as many of them as we can. Now, I'd like to introduce Andre Muller, Product Manager for Uncle at Unchained Labs. Hi, Andre. Today, Andre will walk us through how to use Uncle to test protein stability in thermal ramp experiments with the new isothermal and out-of-the-box applications for Uncle. He'll present data for 2 proteins and across several different formulations. And now I'd like to hand it over to Andre. Andre, how are you doing this morning?
I am very well. Thank you, Kevin. And I'm excited to tell everybody about what we did with Uncle in software version 6.0.
Yeah, glad to hear it. I'm excited to see the presentation. Good luck.
All right. Thank you very much for this introduction. And thank you all for joining me this morning for my presentation that I titled, See Which Proteins Like It Hot with the New Isothermal Applications in Uncle. When you're working with proteins and you want to test proteins for their stability, you usually run a thermal ramp. Thermal ramps are quick, about 2 hours, give you a lot of information about the melting and the aggregation behavior of the protein, and allow you to narrow the list of candidates down so you have fewer candidates to focus your subsequent work on. However, long-term exposure is also something you want to keep in mind, because I'm sure you've all been there. I certainly have. Living in the Bay Area with the proverbial fog, you walk out in the morning, oh, it's not going to be sunny today. I'm not going to get burned. I don't need sunscreen. And then in the evening, everything is red. Long-term exposure is something to work with, something to think about, something to be aware of. And sunscreen helps. And in the same vein, looking at the isothermal stability of a protein can help you prevent bad surprises later on in the development process. When we are talking about isothermal stability of proteins, what we want to look at really is we keep our proteins at a steady temperature over a long period of time, and we monitor their behavior, their unfolding behavior, and their aggregation behavior. And that's things that you can do with the new isothermal applications in Uncle. Why is this important? Well, you know, what people oftentimes do in developing a protein candidate further is they do a thermal ramp first to narrow down the number of candidates, and then they do the isothermal testing at the very end of the development process. That's because isothermal, as it is oftentimes done, is pretty cumbersome. You have to have a large amount of protein solution. You have to store it. You have to run it, for example, in HPLC to look at aggregation and loss due to aggregation. And all these things make isothermal testing, make long-term storage testing kind of cumbersome. Even accelerated stability testing is not really that super fast. It still takes a considerable amount of time and also of volume. When using the new isothermal applications in Uncle, we open a door to testing both thermal ramping behavior and isothermal long-term behavior at the same stage of the candidate selection process, so early on. It is so easy to run isothermal in Uncle. You can run between 1 and 48 samples at a time so that you can use both thermal ramping experiments and isothermal long-term storage experiments to narrow down your list of candidates. And I think that's really the power of it, that you get access to this very important metric of your protein early on. And what I will talk about in this presentation, I'll give you 2 case studies where we looked at 2 proteins and compare results we have from thermal ramps with results we have from longer-term isothermal exposures. Before talking about that, let me first briefly review what we mean when we talk about protein stability. Proteins, of course, we all know they have a native structure, they have a native fold, and that's in an equilibrium with the unfolded state. So by increasing the temperature, you can push this equilibrium towards the unfolded state. This is what we refer to as conformational stability of a protein. To make things more complicated, proteins also do other things. They can also aggregate, something that we call the colloidal stability. And both the native state can aggregate and the unfolded state can aggregate. So in order to monitor the behavior of protein, to monitor protein behavior, protein stability over time or over temperature, we want to keep both the conformational and the colloidal stability in mind. We want to keep an eye on both of these. And the right tool for the job to do this is Uncle. UNCLE combines 3 different measurement modalities in one instrument. So we can measure fluorescence, we can measure static light scattering, and we can measure dynamic light scattering in a temperature-controlled environment. In terms of the fluorescence, we use 2 different laser systems to excite fluorescence. We use a UV laser of 266 nanometers, and we use a blue laser of 473. That way we can excite both the protein intrinsic fluorescence with the UV laser and potential dyes that you want to use. That's what the blue laser is for. At the same time as exciting with 2 laser systems, we monitor the full spectrum of fluorescence emission of the analyte. So we are very flexible in looking at the protein in the shorter wavelengths or reporter dyes like Cipro Orange in the longer wavelengths. In the 2 case studies I'll show later, we'll cover both of these topics as well. The signals or the light that is scattered from those 2 lasers is what we use in our SLS experiment. Static light scattering is a readout of molar mass. As a protein aggregates, the molar mass increases. So the SLS signal is something we can use to assess protein aggregation over time or over a temperature gradient. We have that SLS data for both of our lasers, so both the UV laser and the blue laser. That gives us a very high sensitivity of detection of aggregation, and at the same time gives us a big dynamic range so we can cover orders of magnitude of aggregation occurring. UNCLE also packs dynamic light scattering. It sounds almost like static light scattering, but is fundamentally different. Here in this case, we look at the diffusive behavior of our analyte, and that is an orthogonal measure of aggregation that you can apply. Temperature control, UNCLE can be set in temperature between 15 degrees Celsius and 95 degrees, and we can do that for a ramp, but we can also, of course, do this for isothermal experiments and keep the temperature steady over longer periods of time. The heart of UNCLE, the sample introduction into UNCLE, happens in the unis. The unis are arrays of 16 quartz cuvettes in an anodized aluminum frame. That anodized aluminum is there to make sure that the temperature conductance is high, so the temperature of the sample is what you've actually set. And these cuvettes have a volume of 9 microliters. They're open on both ends, really easy to load. Capillary force sucks the sample right in. And then these unis are clamped in the blue uni frame with silicone seals. So these silicone seals are consumables, and they seal off the quartz cuvette, and you don't have to worry about evaporation. The 9 microliters of your sample are safely sealed in the uni, and then you can use that as in your temperature ramp or also in your isothermal experiment. When you run a protein in a thermal ramp, so in this case here, you see individual spectra building up. We have 1 spectrum recorded for every degree in our temperature ramp from 15 to 95, so 80 spectra here in this case. And what we're seeing as this temperature increases is that the protein unfolds. And you see that the fluorescence spectrum changes. The maximum, first of all, gets lower, and it shifts to the right. It shifts to longer wavelengths for this protein. That is because the aromatic amino acid residues that are responsible for the autofluorescence of the protein, the phenylalanines, tyrosines, tryptophans, are usually buried on the inside of the protein in a hydrophobic environment, and they show fluorescence. As the protein melts and they are turned outside to the hydrophilic environment that the protein is in, their fluorescence behavior changes. And when we monitor the fluorescence in the temperature gradient, we can assess unfolding that way. This shows also the full spectrum of fluorescence of UNCLE. So we record from 250 to 720 nanometers. I cut this off a little bit here because it's just the baseline, but you can look at the protein intrinsic fluorescence here in the blue section. If you had a dye in here, you would see that over here, and I have an example for that coming up later. This is the raw data that UNCLE delivers, so the spectra, and then we process that data to a graph that looks something like this. We have our fluorescence here on the left y-axis. The x-axis is the temperature. This is a temperature ramp experiment. And we have our static light scattering in green on our right y-axis here in this case. What we're showing for fluorescence is what we call the BCM, the barycentric mean. That is the spectral center of gravity of our fluorescence emission. It is the wavelength that separates the area under the curve in 2 equal halves. With this kind of analysis, we integrate over the entire peak of the fluorescence emission, so about 130 wavelengths, which gives us a really high signal to noise ratio and a calm signal. So if we follow this, we can see how as the fluorescence emission maximum shifts in wavelengths, we see that represented here in the curve. And then there are 2 inflection points in this curve, which the software determines by looking at the differential. Those would be the two melting curves, the two melting points, sorry, Tm1 and Tm2 of our analyte. That is what we want to find out in our temperature ramp. At the same time as looking at the unfolding behavior, we also get a glance on the colloidal stability, because the static light scattering signal is rather boring, it's rather flat, and then at around 80 degrees that starts spiking, because that's when the sample starts aggregating. This aggregation for this specific sample here happens in concert with the Tm2, with the second melting event. So much the introduction, so much as to the theory of what we find out in a temperature ramp. Let's take a look at the first case study. In this case, we have a monoclonal antibody, commercially available monoclonal antibody in three different formulations. We have the no salt condition in green. We have low salt, 50 millimolar sodium chloride in blue, and we have high salt, 250 millimolar sodium chloride in yellow. Otherwise, the buffer that the system is a 25 millimolar histidine buffer of pH 7.4. So when we look at these three formulations that are varying only in their salt content, we look at the melting behavior, these three formulations show pretty much comparable, similar melting behavior. So it's varying, melting points vary between 69.5 and 70.4 degrees Celsius, so about 1 degree difference. The high salt condition in yellow seems to be slightly less stable than the no salt and the low salt condition. When we look at the aggregation behavior, and I forgot to mention this earlier, but we measure these two parameters at the same time in the same volume. So the sample is in the uni, and we record static light scattering and fluorescence concomitantly, same time, same sample, same temperature point in this gradient. Looking at the aggregation behavior, we can see that the low salt in blue, let me put the arrows in for the actual aggregation points. So the low salt condition, 50 millimolar salt, starts aggregating first, and the no salt and high salt conditions, they start aggregating a little bit later. These two aggregation points are about 1 degree different. This one is 66 degrees, so this is about 7 degrees lower. So there's significant destabilization in terms of aggregation of our sample in the low salt condition. But differentiating between the no salt and the high salt is going to be difficult. That's what we can learn from the temperature gradient. As I was mentioning earlier, we also measure DLS. So let's take a look at what that shows. And our DLS experiment actually confirms that the sample aggregates in our thermal ramp. When we look at the DLS spectra that were recorded, or the DLS signal, I should say, it's not a spectrum, at 15 degrees, we see that the monoclonal antibody shows a typical diameter of about 10-11 nanometers. And then as we have ramped the temperature up to 95, you can see that these diameters have increased to more than a micrometer. So DLS confirms that our sample has aggregated and confirms what we saw from the static light scattering signal. Now, what can we learn about our monoclonal antibody in an isothermal experiment? So in this case, we have our monoclonal antibody, we incubate it at a given temperature over long periods of time, and we see how our fluorescence and our static light scattering signal will change. We can also look at the dynamic light scattering signal, of course. Example data. So this is not quite the case study yet. I'll get to that in a second, but let's look at some example data here. We also see that if we look at the fluorescence in blue on the left y-axis, that the BCM value shifts. And this is an isothermal experiment over 24 hours at 58 degrees. And at the same time as the fluorescence signal is monitored and changes, we also monitor the, same time as the fluorescence signal is monitored and changes, the static light scattering signal is also monitored and changes, indicating that the sample is aggregating. So again, in UNCLE, we measure fluorescence and static light scattering at the same time and can deduce what our sample does in this isothermal experiment. This experiment was run at 58 degrees Celsius. And I think one of the most important questions when running an isothermal experiment is, how do you want to design it? How do you choose which temperature you incubate in? Some people like using melting temperature -5 degrees. Other people use 42 degrees, 47, 60 degrees, because they have an incubator set at that temperature. It's really quite flexible, and there is not really any consensus on how you would want to do it. So for our experiment, what we did is we looked at our melting and aggregation temperatures and then chose 60 degrees as a temperature for our isothermal. That's about 10 degrees lower than the melting temperatures, and it's about 6 to 8 degrees lower than what we saw for aggregation. What I think is really one of the strengths in UNCLE is that these isothermal experiments are so easy, so you could actually run several of them, one day at 60 degrees, next day at 65, next day at 55, and really find out what the ideal temperature for your isothermal, longer term isothermal is. So you do like a scouting experiment. In our case, we chose 60 degrees and we actually did see something. So let me show what we found. So looking at the static light scattering intensity from a monoclonal antibody, and this is one at 266, so using the UV laser, we see that the low salt condition in blue here, 50 millimolar salt, starts aggregating first, and the high salt condition and the no salt condition start aggregating later. So until about 3 hours, they behave similarly, and then we really see a difference between the two conditions. So by running a 6-hour isothermal experiment at 60 degrees, we can really show that although the aggregation temperatures between yellow and green, between high salt and no salt, are only different by 1 degree Celsius, the aggregation behavior in the isothermal experiment over 6 hours really shows us which is the most stable formulation is. As I was mentioning, we are not only measuring the static light scattering at 266 nanometers, we're also measuring at 473 nanometers, and that result confirms what we saw for the short wavelengths. Also here, the aggregation of the low salt condition, 50 millimolar salt in blue, is occurring first, and the most stable one is the no salt condition here in green. The new isothermal applications in UNCLE also allow you to determine rate constants. I'm showing this down here. So for the blue condition, the low salt condition that shows the highest aggregation, the K1, the rate constant, is the lowest value. So we also, in addition to looking at the graphs by eye, we also have a mathematical metric for the aggregation in the form of the rate constants. Isothermal experiments like this can take a lot of time. So in this case, it only took 6 hours, but you could in principle devise an isothermal that takes several days, takes up to a week, and that kind of sort of locks in your instrument for the duration of that experiment. But because isothermal testing takes time, and because we know that our samples are safely sealed in the uni, we thought it might be really nice to have another set of applications in UNCLE that we termed the out-of-the-box apps. As the name suggests, you incubate outside of UNCLE. You take your sample, read the signal, dynamic light scattering, static light scattering, fluorescence. You take the uni out, put it in an external incubator, incubate it there as long as you like, put it back into UNCLE and add another data point. So the file, the results file, is not locked. You can add, you can append data points and evaluate, analyze that data together, and when you have all the data points in that you would like to have. And also, you're not tied in terms of the temperature, the timestamps. You can choose how many hours you want in between the individual reads. What does this look like in practice? So here is an example of our monoclonal antibody. We measured static light scattering at 473 nanometers, so aggregation behavior at time point 0, at 20 hours, 40 hours, 60 hours. And again, we can clearly see that the low salt condition in blue 50 millimolar salt shows aggregation that starts sometime after the 20-hour time point. And we can grab that, we can measure that with our out-of-the-box experiment. For the 20 hours between those reads, UNCLE is free for other things. So you can start an out-of-the-box experiment for isothermal, take your sample out, put it in an incubator, and then use UNCLE for the time being for other experiments like a KD run, a B22 measurement, or a thermal ramp for other researchers or other projects. So it gives you a lot of flexibility in how you use your instrument. We can do this OTB out-of-the-box experiment not only for static light scattering, we can also do this for dynamic light scattering. So here included DLS in this daily snapshot, time point 0, time point 20 hours, time point 40 hours. And we have one light blue sample here kept at 4 degrees, and you can see the 12 nanometer diameter of that IgG remains constant in the fridge, but at 60 degrees we see clear increase. So this out-of-the-box experiment gives you a good way of following the aggregation of your sample. For our A monoclonal antibody, here's a summary. All the aggregation metrics agree. So if we look at the aggregation from temperature ramp versus the ones from the isothermal experiments and the OTB out of the box, we can see that the low salt condition really is the worst in terms of aggregation. And if you had to choose one, it's probably a 25 millimolar histidine at pH 7.4 without salt is going to be the best one that you can look at. That concludes the first case study. Let's take a second case study into account here, and that used RNase A. RNase A is a small protein, about 17 kilodaltons, and it's very low in aromatic residues. So if we look at the fluorescence, here is the monoclonal antibody we just had with the fluorescence after 266 nanometer excitation, and here's the RNase A. You see it's a much lower fluorescent yield, and if you looked at the BCM curve for RNase A, it'd be pretty flat. It doesn't show much change because there is just very few aromatic residues in here that would be usable in intrinsic protein fluorescence. What you do in this case? Well, we can use a reporter dye. So we used Cipro Orange in this case. Cipro Orange is a dye that interacts with hydrophobic protein patches. So as the protein unfolds, these hydrophobic patches are presented. Cipro interacts with those and increases its fluorescence. So as you see that here on the right side, if my pointer moves with me, we have the folded protein where Cipro Orange has nothing to interact with, so there's very low fluorescence yield. But as the protein unfolds, or is unfolded, I should say, we see a much higher fluorescence yield from the Cipro interacting with the hydrophobic patches of the protein. So when we look at thermal ramp experiment using RNase A and Cipro Orange, this is what we see with our three formulations, the same formulations as before. We see no difference in the melting behavior between those three formulations, and we also don't see any aggregation happen. So in terms of RNase A, there's really no way we can judge which of these formulations is better and which one is the one we're going to use for further optimization studies. So what we did is we also took this analyte here in an isothermal experiment. And what we actually see here is we see aggregation that starts around after 10, 11 hours. In the no salt condition in green and in the low salt in blue, we can see clear aggregation occurring. This is looking at the 266 nanometer light scattering intensity, whereas in high salt, it remains flat. So no aggregation in high salt, aggregation in no salt and in low salt. So in this case, we need the isothermal experiment to really be able to differentiate between the different formulations. We also, of course, wanted to try the new out-of-the-box app for this analyte. So this is the static light scattering. We look at the Z average diameter over 3 days, measured once a day. And you can see that in high salt, confirms what we saw from static light scattering. In high salt, it remains flat, whereas in low salt and no salt, here in green and blue, we see significant aggregation that is already visible almost after the first day. Again, in OTB experiments, out-of-the-box experiments, you are flexible in staggering your data points whatever way you want. The files themselves are time-stamped, so the instrument or the software will keep track of the time elapsed. But for these 24 hours between those reads, you can use your instrument for other purposes. So summarizing the second case study of RNase A, only the isothermal experiment is able to rank the different conditions. The ramp rate doesn't give, the ramp doesn't give us any difference. It looks good in all cases, but looking at it isothermally, we can really differentiate between the formulations and see that only the 250 millimolar salt condition is really good and something that we want to look into further for further refinement of our formulation. So to summarize this, UNCLE, the first all-in-one stability platform, has a set of tailor-made isothermal stability tools, both the regular isothermal tools and the out-of-the-box tools that allow you to start using long-term stability testing early on in your candidate selection process. We, of course, retain what we had before, the Tm and Tagg applications. We can still run DSF applications. We can also take a look at viral capsid stability. And we also actually have an isothermal application that is specifically coined towards viral vectors. Not the topic of this webinar, but we'll talk about this in the future. You can also still use UNCLE's DLS for a DLS with polydispersity analysis or combine it with a thermal ramp. You can look at colloidal stability parameters like KD, B22, the second viral coefficient, or G22. You can use UNCLE to look at thermal recovery, viscosity, and also at isothermal chemical denaturation experiments. So in with all this, Uncle is really your lifeguard at the beach. It'll watch over your 48 samples for 2 hours. It'll also look over them for a day or 2 days and tell you when it's time to put on sunscreen. Uncle is your all-in-one protein stability platform. Make sure that all of your analytes behave the way, or you know how your analytes will behave. And with that, I'm going to be happy to answer any questions that have come on. Thank you very much.
All right. Thank you, Andre, for taking us through how to use Uncle to check conformational and colloidal stability of proteins in both thermal amps and when we're detecting TMs and Taggs, and how to take a look at them isothermally too. I thought it was particularly interesting looking at that RNA example, where, you know, thermal amps are great. It said, hey, all of these look good. And then you just really needed that extra isothermal layer to start to distinguish different formulation conditions.
And I mean, we've been using it in lab a fair amount now, and it's interesting how sometimes the isothermal adds so much more depth to the results. Tm and Tagg are great parameters to rank candidates with, but looking at how they behave over longer periods of time is a really cool and really powerful tool. So I'm excited that we have that available to our Uncle users now.
Mm-hmm. Yeah, it's kind of a natural progression, bringing that accelerated stability testing earlier into the screening phase. All right, so we have some great questions that have already been submitted. For those of you out there that still have a question that you want to ask, you can submit it by entering it into the Q&A section of your Zoom navigation bar. So let's get started here at the top. So Andre, the first question, how flexible are the new isothermal apps in Uncle?
I would characterize them as very flexible. So first of all, we have 3 different isothermal applications. We have isothermal that gives you full flexibility to focus on either the protein intrinsic fluorescence or other wavelengths. So you have full flexibility of which laser you want to use and also where you want to focus your analysis on. Then we have an isothermal for Cipro that is coined towards using Cipro orange, so only using the blue laser, only analyzing in the Cipro typical X emission range. And we also have a isothermal capsid application that would be looking specifically at CyberGold, the readout that we use to look at genome ejection from the viral capsid. So those 3 give you a lot of flexibility there. And then we also have 2 out-of-the-box apps, one that allows you to choose whatever parameter you want to look at, and one that is more in the dye range of analysis. So 5 different applications tailor-made for you to use. And also when it comes to the rate constant algorithms that I was mentioning earlier, they are able to cope with monophasic, biphasic, and triphasic behavior of your analytes. So not only are the apps themselves flexible, also the analysis algorithm is very flexible. So I would say, give it a try it out. It's very flexible, and I think you like it.
Okay, great. So you mentioned it very briefly, but we have a question on it. Can you talk more about how to use those isothermal apps to study AAV and other viral vectors?
Sure. So people that are familiar with the Uncle platform will know this. Otherwise, I'll just introduce it. When you go through a temperature ramp with an AAV, you see behaviors of the capsid protein, where the protein unfolds and where the protein starts aggregating, but you can also see at a lower temperature than where the protein changes, usually a time point where the genome is being ejected from the capsid. And for the isothermal behavior of the AAVs, you can use the new application to look at that. So how long is the capsid, or is the capsid leaking DNA in an isothermal experiment over several days, or is it keeping it in? So just like isothermal for protein can give interesting information about the stability of the biologic, isothermal can also give interesting information about your AAV and allow you to look at like how long can you actually keep your AAV at room temperature before you have a significant loss of your payload.
Yeah, absolutely. Can you briefly go over any other changes introduced in the new software?
Uncle 6.0 it's a result of a software project. So of course, we also took in feature requests that we have from our users out in the field, feature requests that we had internally. We fixed bugs that we knew were in the software. But I think what is most striking, and something that users that are familiar with Uncle will also enjoy, is that we have new colors and new behavior of the colors for the samples. They save automatically now, and we have introduced something that we call replicate groups. So if you run a sample in triplicate, you can now show the trace of the triplicate with shading for your standard deviation. So a much more natural feeling interaction with the data you've generated. And that's going to be, I mean, I really like it, and it's fun to use, and I'm hoping that you like it too.
Okay, yeah, just adding a lot of joy to using that software. So that actually dovetails nicely with this question. Does it require a software update? I imagine that answer is yes. And if so, how is this added to the system?
We have sent email. I've sent emails to all of our Uncle users to tell them about how to go about this. If you haven't received an email because you're not in our database, maybe somebody left your company and you're now the Uncle Power user, go to our website, and the Uncle product page at the bottom of it, it has the Uncle software upgrade. Submit your information there and we'll be in touch and let you know how to upgrade the software. It is solely, there's no hardware changes. It is only a software upgrade. So 5 minutes and you'll be set to go with Uncle 6.0, super smooth. And everything you know and love from Uncle 5 is still there. And I think we made some changes that make it even more fun.
Okay. And then just a kind of a experimental design question for the isothermal studies. We had a couple in there. Can you talk about the protein concentrations that were used?
We used our proteins at a typical, I think for the IgG, it was 1 milligram per milliliter. For the RNase A, it's a bit of a smaller protein, so we probably went a bit higher, probably 2 or 3 milligrams per milliliter. The sensitivity of Uncle is not changed in the isothermal apps. I think what you would want to look out for if you go on a long-term experiment is really like maybe the aggregation is so much that it saturates your detector, so you might actually go a little bit lower. But generally, the same range of concentrations that you have used for Tm and Tagg before, so the milligram per milliliter range for an IgG is going to be really good.
Okay, and looks like we're just hitting the bottom of the hour there, just ran 1 minute over. So I think with that, we'll wrap up and say thank you to all of you who joined us today. If you'd like to have a deeper conversation with our team, please do get in touch with us at info@unchainedlabs.com or learn more from our website, unchainedlabs.com. We would love to connect with you. I would love to talk science with you. Thank you again for attending our virtual seminar, and I hope you have a great rest of your day.
Thank you.